So in this problem, we are given a vector y and then another vector u, and we're asked to express y, to sort of decompose it into the sum of a vector in the span of u, which is going to be a vector that's along the vector u, and a vector orthogonal to u. Now I'm going to draw a diagram over here away from the glare. Let me draw a diagram of what we're trying to do. So I'm just going to draw like a random vector and call this y. So here's this vector y, and we want to write it. Let me draw another just random vector. I'll make this one longer. So let's call this vector u. It looks like it'd be longer, 4, -7. Where we want to express y as the sum of a vector in the span of u. So let me talk about that for a second. So something in the span of u, that means that it needs to be a linear combination of, well, just the one vector u. So that would mean that it's some scalar multiple, let's say c times u, this vector in the span of u. So the goal is to express y as a vector that's a scalar multiple of u, so it's going to be some vector along this line that u lies along. So something like this. This is going to be our vector c times u. There's our vector in the span of u. And a vector orthogonal to u. I'm looking around for what color I can use. I'm just going to have to use black here. So I'll call this z, since that's what I called it in the written explanation. So there's our vector orthogonal to u. So the one orthogonal to u is the one I'm calling z for now. Okay, so the goal here is to come up with these vectors cu plus z that's equal to y. And actually, let me write that equation. So we want to come up with vectors cu and z so that y is equal to cu plus z. Okay. We're given the vector y, we're given the vector u. So what we need to solve for is this scalar multiple c and the vector z here. Z, sorry. This is the vector z. So we're trying to solve for the scalar multiple and then the vector z. Well, let me point out, if we can find c, then we'll know everything in this equation except for z, so then we could just subtract cu from both sides to solve for z. So we're going to find z second. I'm going to first focus on finding this scalar multiple c, and I'm sorry it's in that glare. Anyway, all right, so I'm going to take this equation. I'm going to take the inner product of both sides with u. So I'm going to write y dot u. Let me use the purple here. Y dot u is equal to cu plus z dot u. And then I can distribute that inner product. So y dot u is equal to c times u dot u plus z dot u. And distribute here. Okay, now look for things that are orthogonal, because then we can get rid of inner products. So orthogonal to u. Z is orthogonal to u. So because z is orthogonal to u, that's the way we're designing this. See how z sticks straight out of u. This inner product right here is 0. And so now we have y dot u is equal to c times u dot u. And so now to solve for the scalar c, we can just divide, let me write this equation. Y dot u is equal to c times u dot u. And so now we can divide both sides of that equation by u dot u. This is gone. And there we go. So there's our formula for c. Now the vectors y and u were actually given here. We have values. So now I can find this scalar c by taking y dot u. So here's y, here's u. I guess I'll copy them down here. So y is this vector 2, 3, dot u is this vector 4, -7, divided by u dot u. So that's 4, negative 7, inner product with itself. So that's equal to 2 times 4 is 8, plus 3 times negative 7, so that's negative 21, over 4 times 4, so 16, plus negative 7 times negative 7, so that's 49. 8 minus 21, so that's negative 13, over, this is 65. And that fraction reduces, you can divide top and bottom by 13, that reduces to negative 1 over 5, if you divide top and bottom by 13. Oh, and I hope you guys can see. But so the scalar c, we just discovered, is negative 1 over 5. Trying to write that nice and dark. We now need to find this vector z. So like I mentioned a second ago, let's get rid of this. If we subtract cu from both sides of this equation, we'll have z by itself. So the vector z is equal to y minus that vector in the span of u. So in this case, y is the vector 2, 3. C is negative 1/5. U is the vector 4, negative 7. So this works out to, let's see. Well, I guess I'll come down here. Oops, there's no line here. It's not a fraction. 2, 3. So if the double negative here, so this is plus 1/5 times 4, negative 7. So that's plus 1/5 times 4. And then 1/5 times negative 7. And so to do the arithmetic here, you'd want a common denominator. So instead of 2, I could express that as 10 over 5. That's 2, plus 4 over 5. And then instead of writing this as 3, I could write it as 15 over 5. That's 3, minus 7 over 5. And so I get 14 over 5, 15 minus 7, so 8 over 5. This is the vector z. So now we've got a vector z, and we've got a vector c times u is negative 1/5 times 4, negative 7. So that's negative 4/5, positive 7/5. And what we could check is, well, a couple of things. Let's see, what were we after? Y is supposed to be the sum of these two vectors. So if we wanted to check our answer, we could real quick check the sum. So if you combine these, you get positive 10 over 5, which is 2. And if you combine these, you get 15 over 5, which is 3. So the sum is equal to y, where these vectors are orthogonal to each other. C, U, and Z are supposed to be orthogonal. So let's check the inner product. If I do 14 over 5 times negative 4 over 5, that would be negative 56 over 5. And then multiply the second entries, you get positive 56 over 5. So the inner product is 0. So it all checks out. This answer looks good.